Catherine Breslin. I'm with Cobalt Speech and Language. I'm really excited to be here at the L3 AI conference from Rasa, and I'm really happy you invited me here to talk about scaling voice assistants. So before I talk about scaling voice assistants, I firstly want to focus a little bit on what do I mean by voice assistant and what's inside a voice assistant and how does it differ from a chatbot. So when people think about voice assistants, the first thing that springs to people's mind is smart speaker devices. So these have been very popular in the past few years. And a smart speaker device is a complex pipeline of different technology underneath it, which allows it to listen to and to interpret and to respond to requests that you make of it. So you might say, hey, computer, play me some music. And the smart speaker device will listen to you, will understand what you're asking for, and it will play some music for you. So underneath the smart speaker device, the interface, is, like I said, this pipeline of different technology. And most of this technology is based in machine learning, so it's learning from data. So speech recognition, language understanding, and text-to-speech all learn from data how to behave. So the first thing that happens is you have an automatic speech recognition, which is going to understand that wake word, that phrase that you said, like, hey computer, to wake it up. And then it's going to understand the request that you've made. It's going to convert that audio into words. So play me some music. The next step is language understanding, which is going to interpret that one request and say, well, what does the user actually want to achieve? So I might say, play me some music. But I might equally say, I'd like to hear some music, or please play me music, please music. So there's lots of different ways I can ask for that one simple request. And so the purpose of the language understanding component is to bucket all of those into one intent, one category of request. There may be a dialogue management component to this, which comes into play if I don't, for example, give enough information in my request. So perhaps in my request where I say, play me some music, the system wants to know what sort of music I want to play. So it will ask back, which artist would you like to listen to? And this is a sort of small back and forth conversation, which is controlled by a dialogue management module. And then finally on the output, there is a text-to-speech, a voice, which is going to speak out and respond and say, here is some music by the artist. So, like I said, all of these different components here are mostly rooted in machine learning technology. So they are learning from data how to behave and how to act and how to respond to language. And they all have to work together in this pipeline, so that when you say your request, it flows through all of these different components and performs the action that you've asked for. So, of course, smart speakers are one of the most popular customer-facing applications of voice assistants and voice technology. But what we're starting to see now is a proliferation of specialized voice assistants, so much more narrow domain, much more custom-built voice assistants for specific applications. And there's some different examples here. So, for example, in banking, we might find a bank has built a voice assistant into their app, which allows you to do some of your handling of your financial affairs by voice. When it comes to customer service, there is some companies who are looking at using this technology in order to automate their customer service. So some of the simple things that people phone up about to their call centers. And in this case, we are not putting that technology on a smart speaker, but at the end of a phone line. And aside from that, it's roughly the same technology. So being able to handle voice inquiries automatically. And this is something that a lot of companies are interested in, because they're interested in the efficiency savings that can be gained by automating quite a lot of the routine customer service inquiries. And then there's a whole host of other narrow applications that we might think about using voice assistants in, like healthcare, legal advice, maintenance, travel assistance, tickets, music. All of these sorts of much more narrow use cases might be great use cases for custom, small, specialized voice assistants. So now I've talked about what I mean by a voice assistant. Let's talk a little bit about scaling voice assistants and what it means to scale this technology up. So we're talking about after you've built and deployed your system, and most people, when they talk about scale, then are talking about getting more users. Can we scale up our software so that it can handle more and more requests, so that more and more people can use it in parallel? And so the most obvious thing here is in scaling your production infrastructure, your software stack, so that it can handle multiple requests. But the focus of my talk is less on the software side, because I think there's many more great talks about that than there is about the scientific side of scaling up to new users. So I want to focus on what happens when you get more users using your system. And what I've generally seen in this case is that you start to get many, many more different kinds of requests than you ever anticipated. You start to see much more variation in your input. You start to see people ask all sorts of things in all sorts of different ways that you didn't really anticipate. And you need to make your system more robust to all of these variation in language than you have done before. And when you're dealing with language, one thing you can do is you can just think ahead of time of all of the things that people might say to your system. But it's really hard with natural language to predict all of these ahead of time, because people have very different ways of phrasing things, and you don't always know what they'll be before they start using your system. And so you can't ahead of time just list out all of the ways that somebody will talk to your system. That's just an infeasible way to approach the problem. And this is where machine learning becomes really important in understanding language, because then you can build your systems which learn some of the patterns of the ways that people are talking, and they can use that to respond to things that they've never heard before. And at the same time, as your user base grows, you have to be able to respond to variation that's not just in the way people say it, but who the people are. So that may include the accent, age, or gender, things like this that cause people to speak differently. And so you have to be very cautious, very proactive in this case, to make sure that your system is actually being trained on a wide variety of data, so that you are not limiting the demographics of the people for whom it works. So if you are building a system which is only going to work for a small group of people, and it doesn't work for large amounts of your users, they're not going to continue to use your system. So here it's a case of being proactive and making sure that you are ahead of time capturing all of these different demographics, all of these different variations in the way that you're building your system. Of course, I talked about voice assistants being a pipeline of different technology. Yeah, so we have a speech recognition system and a language understanding system and a text-to-speech system. And we can test all of these in isolation for all of our different users. But as we get more and more users, it becomes more and more important that we are testing the whole system end to end, so that we're making sure that the entire system works as it's intended to. As you get more users, they will report more bugs, more errors. It will go wrong in new and exciting ways. So making sure that you are end-to-end testing your system and making sure that your speech recognition component plays nicely with your language understanding, and that plays nicely with your text-to-speech system. You have to test the whole system as one, as well as testing each component in isolation. A second way that we think about scaling voice assistants is not in the number of users, but in the number of features and the number of things it can do. Now, I talked a little bit before about how we model language as intents. We're going to bucket the requests that people have into different categories. So we might have a category of intent, which is playing music or asking for the weather forecast. And this is called an intent, this category of request. The other thing that we're looking for when someone is speaking to our system is the slots. So slots are the entities that they're asking about. So if they ask for the weather forecast in a particular city, you say, what's the weather forecast in London tomorrow? London is of interest, but I could equally well say, what's the weather forecast in Berlin tomorrow? It's the same language effectively, just a different slot, a different city in there. We might also, when I say play music, we might say play music by Sting or play music by Madonna. We've got different artists in there. And so when we're adding new features into our voice system, we're usually adding new intents and slots. We're expanding the number of intents that we look for and the number of slots that we can recognize. And so adding in new features and new functionality, it's great to put yourself in the mind of your end user and think of the sorts of conversations you'd like them to have to help you design these new intents and slots that you want to add into your system. But inevitably, as you add new intents and new slots, you'll find that they clash somehow with the features that you've already built and deployed and that your customers are already using. So take an example of our smart speaker that plays music. And if I say to my smart speaker, turn it up, simply just turn it up, I'm almost certainly asking to turn the volume up, because that makes sense in the context of an assistant which is playing music. But now suppose I expand the functionality of my smart speaker so that it is also able to control devices around my house. It's got some smart home capabilities, and I connect my air conditioner to it, or my central heating. And now I say turn it up. In this case, the utterance becomes ambiguous, because I could well be referring to the temperature in my house, and I want it to be warmer rather than turning the music up. And so this sort of ambiguity comes in a lot as you are adding in new features, and you will always see clashes like this, which have to often be resolved with various discussions between product teams and technical teams. And often it's not simply a technical solution to these, but driven by some of the business requirements that you're trying to achieve. And in order to add new features and new intents and new slots, if we're using machine learning under the hood to recognize and to categorize intents and slots, we also have to have data in order to train the systems. Now, one way that a lot of people build data for language systems is by generating data, synthesizing data, by writing some rules about how people might say things and generating data from that. This has advantages in that you can quickly generate quite large amounts of data that you can use for bootstrapping your system. But the kinds of things that you will come up with ahead of time are not always what your users will actually say once you deploy the system to the real world. And so there's a tension here between the data that you really want to use for training your system, which is real world data. But we have to be cautious about users and the system that we're deploying to them and the use of their data. So ensuring that we are getting informed consent for using people's data, that we're in compliance with all the data handling laws, and that we're doing this in the appropriate ways, and we're not simply just harvesting data. So it's necessary here to be transparent with the users about how you're actually going to use their data in order to improve the system. And a final point about adding in new features to the system is that we evaluate machine learning systems by computing their accuracy on a large set of testing data. And so if we're adding in new features to our system, we are not guaranteed that the performance will remain consistent as we add new features in. We're not guaranteed that if we add a feature in, it won't somehow clash with an existing feature and degrade its performance. And so you run the risk when you add in a new feature that you make one of your existing features perform worse. So in order to mitigate this and to understand the issue, here we really need to be rigorous about accuracy testing, making sure that we are not degrading system performance when we release new features, and make sure that we are testing new features alongside the old features that we already have. And this accuracy testing forms a big part of our build and release cycle for building new features and releasing them into a new system. And the third dimension I talk about when it comes to scaling up is to do with language. So an assistant that is trained in English and works for English, and English requests will obviously not work if we speak to it in German. And so in order to build new languages, we have to consider firstly what we can reuse from the existing languages and what we have to build up from scratch. So the infrastructure that we use for building and testing our models can all be shared between languages, just the simple mechanics of building our system and testing it and deploying it. The intents and the slots that we use, they can often or usually be reused between languages. But where we diverge mainly is on the data that we need to build a new language. So if you are building a speech recognition system for German, you need German data to train and test it rather than English data. And it may sound obvious, but if you have built a system in English and invested a lot into it, you may not find the collecting the same amount of data in a new language in German is easy to do, or is within budget. So there is machine learning techniques we can use, like transfer learning. And transfer learning is a way of transferring knowledge from one task to another task. So we can think about using transfer learning to transfer what we've learned in an English model to what we've used in a German model. And transfer learning can be used across the pipeline here. So we can use transfer learning in the speech recognition system to transfer our speech recognition models from English to German. We can try using it in the NLU pipeline and in the text-to-speech pipeline. So we're looking at taking what we've already learned about English and the way people talk about things in English, and collecting then much less data in German so that we can build our German system. And this allows us to build and deploy systems in a new language without such strong data requirements as we had for our initial language, which can be a great way to build new languages. But languages, I said that some of what you've learned can be shared, but there are some interesting characteristics of different languages, and not all languages are like English, and so there's various different things that we have to take account of in different ways when we are building systems in new languages. And so I wanted to show you some examples of some of the different characteristics of languages. So firstly, German. German is a language that has the ability to build up compound nouns by concatenating different words together. And this example here of insurance companies providing legal protection is a single word. But we may be interested in our slots in our system being only part of this word. So we may be interested in insurance companies that provide a different type of protection. And so we have to be cautious that our slots in German may be parts of words rather than full words. Japanese is a language which is written without spaces, in contrast to English, which is written with spaces between the words. And so the concept of a word in Japanese is very different from the concept of a word in English. This text here is "Ohayo gozaimasu," good morning, in Japanese. In order to split this into words, we introduce another component into the system, a tokenizer, which is going to insert those words, those spaces between the words. It's going to make a very informed guess as to where the word boundaries are in Japanese text. And obviously, this can help us apply the same technology as we've used for English, but it does also mean that there's another place that you can introduce mistakes, because that segmenter, that tokenizer, is not going to be 100% accurate. Mandarin is another language which has the concept of tone. A tonal language is one in which the way you say something, the intonation, affects its meaning. So in English, it's the phonemes that you put together to make a word, make the meaning of the word. But in Mandarin, it's the phonemes and the tone, the intonation. So whether you say something with a rising intonation or with a falling intonation or a neutral intonation, these things all change the meaning of the sentence. And so for Mandarin Chinese and other tonal languages, we have to build our speech recognition systems that use this information about intonation as well as the information about the frequencies in the sound in order to be able to understand the difference between a sound with a rising intonation and a sound with a falling intonation so that we can get the speech recognition right. And my final example here is from Korean. And Korean has a much more complex system of formality than English, which means that the way you say something differs very much depending on whether you're talking to somebody who's more senior than you, someone who's your peer, or perhaps a small child, or a close friend. And so this verb, to lie down, has different meanings, or different forms, depending on who you're talking to. So our speech recognition system has to be able to understand all of these different forms, but also our text-to-speech system has to know which is the right form to use when it's speaking. So we have to be able to build our voice assistant so that it strikes the right note of formality when it's talking. So I'll show you these examples, not because it's a comprehensive list of all of the differences that might crop up in languages, but just as some examples of the different kinds of language-specific things that we have to take into account when we're building voice assistants across different languages. So I've talked about the different ways that we might scale voice assistants and some of the things that we have to think about when we do so. I want to finish by looking to the future and some of the things that might happen as we move forward in the next few years. So the first thing I think that I see already happening is that this technology is becoming much more customizable. We are seeing tools being built to enable many, many more people to be able to build their own technology in this space. And I think that's great because it makes it much more accessible and allows many, many more people to make use of this technology. And I think this is a trend that will continue over the next years. I also think our voice assistants will start to become much more contextual, in that they will start to understand much more about the real-world context in which they are deployed. Now, if I was to say to my smart speaker, play Frozen, I'm probably asking for the song because the smart speaker is a music playing device. Whereas if I talk to my smart TV and I say play Frozen, I'm more likely to be asking for the film. So understanding this sort of real world context, and not just the real world of how it's deployed, but also perhaps my personal preferences about what I'm asking for. I think these things we'll see much more in voice assistants in the next few years too. And the final point I want to talk about is to do with conversations. So conversation of the type that two people have together is very difficult for us to achieve with a computer. I think we're a very long way off being able to have those sorts of really natural interactions with computers. But we are starting to see many, many more conversational elements come into our voice and dialogue systems in a way that will continue over the next few years. So thanks very much for listening, and I hope to see you at the Q&A.